Hello, and welcome to Whoops, I Rewrote It in Rust. My name is Brian Martin, my pronouns are he, him, and I'm a software engineer at Twitter. I've been at Twitter for 7 years and have been using Rust for 6 years. I've worked on a few open source projects in Rust, including a benchmarking tool, a systems performance telemetry agent, and now I'm working on a cache server. When I'm not at a computer, I'm volunteering with my local search and rescue team, and I'm training my dog Riker to find people who get lost in the wilderness. This talk is framed around caching, specifically distributed key value storage. You can think of it as the standard library's HashMap, but over the network. Cache services are very high throughput and low latency. A single core can do around 100,000 requests per second with sub-millisecond latencies. Caches are used to store frequently accessed items so that we don't need to ask the database for the same thing again and again. This helps protect the database from bursts of traffic and can let the application get data more quickly since the cache is so fast. There are a couple common open source solutions in this space, including Memcached and Redis, which are both written in C. This leads me to Pelikan, which is Twitter's caching framework that we want to use to replace our forks of Memcached and Redis. Pelikan gives us a single codebase to produce multiple caching solutions and to easily experiment with ways that we can come up with solutions that leverage new technologies. We needed to add TLS support to Pelikan so that we could encrypt traffic between the client application and the cache server. I convinced the project maintainer, who's my current manager, that we could probably use Rust to add TLS support to Pelikan. I had the time to work on this, and I definitely feel a lot more comfortable using Rust than C. And we wanted to be sure that if we were going to do it this way, that we would be able to match the performance of the C implementation. There were some previous efforts that made me think this was going to be possible. Back in 2018, an engineer wanted to add a new storage library to Pelikan and decided to try writing it in Rust. The idea was to use the core of Pelikan and provide an FFI wrapper around the Rust storage library. This worked out pretty well. Development was quick, and having a hybrid C and Rust server was workable. This became the first commit of Rust into Pelikan. Super exciting. Then in 2019, another engineer was a bit more ambitious and wanted to try using Rust for the actual server code. They decided to use Tokyo to write the async server runtime, but leverage the C components from the normal cache server for storage and some of the other foundational libraries. But this was pretty neat. It showed we could do a lot more advanced layering of C and Rust together in the codebase, and I was super excited to see that Rust could in fact play a larger role in Pelikan. Performance of cache services is super important. As I mentioned earlier, we expect a single cache instance to support around 100,000 requests per second on a single core, with latencies below 1 millisecond. To ensure this, we typically apply some synthetic workload with a fixed request rate and record the latency for each request into a histogram. Our goal is to hit the highest throughput with the P39 latency below some threshold. The P39 is the 99.9th percentile of the distribution of all the request latencies. So why do we care about this P39 number, this 99.9th percentile? Well, if we only need to make a single request to the cache for some higher level request, then only 0.1% of requests are going to be above the P39. And this is called fan out. If we need to make multiple requests to serve some higher level requests, let's say that we want to load a user profile, that might need 10 cache requests to actually fulfill that higher level thing. With a fan out of 10, we multiply the percentage of our odds of seeing a higher latency. So whereas with a fan out of 1, only 0.1% of requests would see a latency greater than the P39, with a fan out of 10, 1% of requests are going to see the P39. For even the larger things, maybe loading something like a home timeline, you might have a fan out on the order of 100. This means that 10% of the requests are going to see your P39 latency. The key takeaway here is that multiple cache requests for a higher level request causes us to see the tail latency more often than you think. And that makes us care about these percentiles that might otherwise seem like they're way far out in the tail and don't really happen that often. But with fan out, they do. So, we have this implementation of Pelikan Memcached, Twitter's Memcached fork, written in Rust from 2019. It's Memcached protocol compatible. It uses Tokyo and async for its networking, and it uses the C storage library to provide the caching. So the question is, can we use this as a starting point to add TLS? First, we need to do performance testing. And unfortunately, we found there were some performance problems with this implementation. The throughput was about 10 to 15% slower. This means that we'd need 10 to 15% more instances to match the throughput requirements for the cache cluster. That means it's 10 to 15% more expensive to run. On top of that, the latency was 25 to 30% higher at the P39s. This means that we could potentially see timeouts and errors in production. To visualize the benchmarking results, here we're looking at a latency curve of the P39 latency on the vertical axis versus the throughput on the horizontal axis. The C baseline implementation is shown in blue, and the Rust implementation is shown in red. And what we can see from this diagram is that the Rust implementation has a higher latency throughout the whole range of throughputs. Additionally, we can see that the Rust implementation doesn't reach the same throughput as the C version. So this means that the Rust implementation is slower in terms of both throughput and latency. That makes it a pretty tough sell to use this in production. But Rust should be as fast as C for this. Let's see if we can make it faster by taking some steps back. A basic server that you might find in a lot of examples is called a ping server. It's a really simple server that just responds back with the text pong every time you send a ping to it. It has all the basics that you need for a network service, though. It accepts new connections, it parses some requests, in this case either a ping or a quit, and then either responds with a pong or closes the connection. So it's a super simple protocol. We start with a ping server because it allows us to prove out the performance of a design. We have all the same functional blocks as a real service, except we're just not storing any data. But we can add all the things we need in terms of connection and request handling and debuggability and metrics. This is also a great place to start thinking about adding that TLS support that I was supposed to be working on, to prove that the design could easily accommodate both plain text and encrypted sessions. Since I was concerned about making the performance match the C implementation, I wanted to try and make things as equivalent as possible. The C implementation was basically just using epoll on Linux, so we could use MIO as an equivalent and not need to worry about async executors at all. We'd also have a simple event loop just like the C version. To get to a prototype quickly, I used a bunch of foundational libraries that I had been using in other projects. This meant I could focus on getting something built out quickly with a pure Rust build. If I had problems, I could always switch to the C implementations later. I also added TLS support using boring SSL at this point, so I was sure my design would handle both plaintext and encrypted connections. And then we benchmark again. Just like the previous chart, we're looking at request latency versus request rate, and specifically looking at the P39 latency. We can see that these are pretty close. This looked good to submit a pull request and merge into the Pelikan repo on GitHub. Feeling good about this, it was time to move on to what I was actually supposed to be doing. The real goal was to add TLS support to our Memcached fork, to Memcached. So let's try doing that. The primary difference between Memcached and the ping server is that we have a much more complicated protocol. The Memcached protocol has a whole bunch of different requests with variable numbers of fields, and my main focus was on getting all that protocol handling correct and making sure that it performed well. So in order to avoid having to think about the storage aspect of this, what I did is I made a thin wrapper around the standard library's hash map and used that as a stand-in for the storage library. So this allowed me to focus on the protocol and also start forming a storage abstraction layer. So once I had this in place as a prototype, I was able to do some benchmarking and make sure that I was still on the right track in terms of how the thing would perform while responding with actual payloads, right? So responding with a pong, that's only a handful of bytes to respond. But with a cache, we might have items that are much larger that we're responding with. So I wanted to make sure that all the buffering and parsing and response composition was all really good. So I did some benchmarks, and those were looking promising. So we can move on at this point to adding a FFI wrapper around the C storage library and integrating that into this new implementation. But of course, I'd run into some issues at this point. Choosing to use Rust versions of some of the foundational libraries left me stuck in terms of trying to use a storage library which had metrics and logging deeply integrated into it. And we wanted that. We need really good insight into the performance and be able to debug things. So I had a choice at this point. I could either rip out the Rust versions of these libraries and improve the ergonomics of the existing wrappers for the C implementations, or I could maybe figure out some way to make the C library, the C storage library, talk to the Rust implementations of metrics and logging. It really got super gross super fast, and I probably spent way too much time feeling just absolutely crushed by this problem and trying to figure out some way to move forward. Ideas that seemed bad were starting to sound better. Maybe I could rewrite this storage library in Rust. And there were a lot of reasons why I didn't want to do this. The storage library essentially winds up being this place where we run into all sorts of things that aren't super easy to do with Rust. We have self-referential data structures and managing memory allocations to avoid external fragmentation. We've got many linked lists, pointers all over the place, unsafe code everywhere. It just didn't seem like the right thing to do. On the other hand, maybe we could simplify things a little bit. Maybe if we start with something that's only single-threaded, that we don't need to think about concurrent access, that might make it a little easier. Maybe we could just implement the hash table in Rust and use C code to allocate and manage these big blocks of memory. All this wound up being depressingly difficult as well. Luckily, around this time, there was a newer research storage design by a PhD student who was working with us, and this new design was a lot easier to port to Rust. I even simplified that design further and took it back to being designed for single-threaded use, so there's no locking or concurrency things that I might get wrong. Rust does make these things pretty easy normally, but for memory efficiency reasons, I wouldn't have been able to use the Rust primitives for doing locking and concurrency. They use too much memory for this particular use case. But best of all, once I went down this path, I found I was able to manage all the memory from Rust and not have to deal with anything terribly exotic like a custom allocator or anything to make this work. So it was actually pretty straightforward once I started with a different style of storage library. So there were downsides to doing a rewrite, and these would apply to whether I did this rewrite into Rust or C or any other language. It cost me 2 months of work that was essentially duplicating previous efforts. And even at the end of that, I didn't hit exact feature parity. There's more work that needs to be done still. In terms of benefits, though, this kind of caused us to move forward to using this newer storage design, which has benefits for a lot of our workloads at Twitter. Otherwise, we still would have been on that older storage library and not even been able to start tapping into some of these benefits of the new design yet. So this kind of forced us to move forward a little bit. Additionally, during the rewrite, I identified some areas where we could improve this new design even further. And these improvements would help some percentage of our workloads. Not all of them, but enough that this also seemed like a win. And lastly, it helped make it more production ready. It was pretty much a research/reference implementation of a storage library, and having another software engineer come through and take that code and really dig into it helped address some of the things that might have caused us some pain a little bit later. So it's always good to evaluate this kind of stuff and see if there are tweaks you can make to improve things further, or areas where you can clean up and have a second set of eyes really deep into the code. There were benefits purely that came from rewriting this in Rust instead of picking any other language. And really, I've seen this quote before on the RustLang page, but it rang extra true after working on this project. Rust does empower everyone to build reliable and efficient software. The code you produce winds up being high performance, and you're able to code with confidence in reliability. The language has all these awesome features and tools around it, and those really help you write good, solid code. Additionally, zero-cost abstraction winds up making you able to express these things in ways that you might not be able to in other languages. So that's really cool. At the end of the project, my manager, Yao, who's the primary maintainer for Pelikan, had this quote to say about the rewrite and the benefits of Rust. Yao said, "The Rust implementation finally made Pelikan modules what they ought to be, but couldn't before, due to limitations of the C language. This feels exactly right and is just as fast." I think that's really cool coming from someone who is really good at C and has been working in this field for a long time. It's really encouraging to hear that Rust can express some of these things in a way that's a little more elegant and fits better for the particulars of the software. I thought this was really nice. This made me feel good about what I did. As I mentioned before, Rust has awesome tools. Some of the tools that really helped me out a lot in making sure that my code was performant and solid were Cargo Bench with Criterion, doing microbenchmarking of critical components like parsing and the storage library itself and how the hash table works and all these really low-level things. Being able to have microbenchmarks for those critical components really helped me make sure that each of these was very efficient and that as I started making more changes, I wasn't going to have a performance regression. Additionally, I used Cargo Fuzz a lot for the protocol library. I wanted to make sure that through using fuzz testing, I was able to find some edge cases that I hadn't quite considered in terms of malformed requests. So that's one of the really great things about fuzz testing is you don't need to think of all these edge cases yourself. You can have the computer start to discover them for you. And when you find something that breaks your code, you can add a new unit test for it. And this really helped me feel like the protocol was going to be rock solid and that I wasn't going to have any weird crashes in production for having array indexes be flipped around or all sorts of other things that I encountered while I was fuzz testing. So these two things helped me feel a lot better about the code that I was writing. Here I'm showing basically the benefit of the zero-cost abstraction and the traits and type system of Rust and generics, really. So here, what I'm showing is that segcache, which is the resulting cache server, is a combination of the Memcached protocol with this segment-based storage. And we're able to use about 200 lines of code that's a lot of boilerplate, initializing data structures and the runtime and all that stuff. But really, the code between the ping server and segcache are very similar, except they differ in terms of what storage engine they use and what protocol they use. So here we're showing the composability of these things and how we're able to neatly express that with traits and generics. So I thought this was pretty neat at the end. And when we write a new storage library or additional protocols, they'll be just as easy to compose together. Some more testing to show off the end results. Here I'm comparing upstream Memcache in blue with the Rust implementation of Pelikan segcache in red. And I'm going to zoom in on the end of this graph here. At the higher throughputs, we can see that upstream Memcache actually has higher latency than this Rust implementation of a cache. This is super cool because Memcache is really, really fast. So it's neat to see that we can actually meet or exceed that performance with a Rust implementation. So just to sort of wrap up some things with a summary. There's more work to be done. There are two parallel tracks that are going to happen at this point. One is the path to production for this Rust implementation. It needs to get to feature complete. There are still a few odds and ends that we need to do in order to have full feature parity with the C implementation. Once that's done, we'll move on to more testing, deploy a single instance out to production as a canary, and then eventually do an actual deployment. And we think we should be able to do this probably by around the end of the year in terms of having a Rust cache server start serving production traffic, and that's exciting. There's future work to do. Earlier, when comparing with upstream Memcache, I was showing single-threaded performance, but this implementation also has a multi-threaded configuration, and so does upstream Memcache. And while this Rust version of segcache has better performance than our internal Memcache fork, especially when TLS is enabled, it loses out to upstream Memcache in multi-threaded configurations. I think we can close this gap. The performance is good enough for us to deploy to production, but I still want to win some benchmarks. That's always fun. There's additional optimization that we can do probably even for the single-threaded implementation. There are areas that I want to clean up there. Additionally, this work doesn't get us a Redis replacement yet, and that's still one of the things that we want to do. And we'll go back, we'll figure out what the storage needs to look like for that. Need to write a protocol implementation, but we'll be able to reuse all the other components that we have in terms of foundational libraries. And we feel confident that we'll be able to write a Redis replacement for Pelikan in Rust. And then there's all sorts of really cool stuff that I want to play with in terms of this. There's IOU ring, there's user space TCP stacks. There's all sorts of really fun things that we might be able to do to get even more performance out of this. Rewriting has costs and benefits. The extra time could have caused missed deadlines if I was working towards a deadline. Luckily, I wasn't for this. But I was duplicating work that had already been paid for, so that did have a cost. There were benefits, though. The code was easier to work with once it was all Rust. I didn't have to fight with cmake and cargo together. And some new ideas got added to the code, so that's probably a win overall. C and Rust are both very fast. Profiling and benchmarking helped me get the performance to match that of the C implementation, but it did take work. The Rust ecosystem has all these awesome tools that I mentioned before. We have cargo, we have fuzzers and benchmarks and things that help me feel that the code is solid and going to perform well. And then we have tools like Rust Format and Clippy, which helped me make sure that the formatting and that the code was idiomatic, and that went a long way to making the code easier to work with and for my manager to review. And I think Pelikan has a really exciting future with Rust. It seems like we'll be able to migrate the whole codebase to Rust, and I think there's lots of fun work to come. Thanks for listening to my talk, and thanks to all the folks involved in putting together this conference. Feel free to reach out to me with any questions. Bye.